So it's my great pleasure. I was absolutely delighted when our next speaker agreed to come and talk for us today. Professor Ahmad-Reza Sadeghi is a professor at the Department of Computer Science of TU Darmstadt, where he's the head of the System Security Lab. He's also, since 2012, I think, director of the Intel Collaborative Research Institute for Secure Computing. And there's a long acronym that goes with that, but I won't try and read it. He received his PhD in computer science with a focus on privacy protecting cryptographic protocols, something in common with several of our speakers, in fact. But actually, I found there's also a sort of Swedish connection.
Yes, very much.
Prior to joining academia, in fact, Ahmad worked in research and development at Ericsson. And there's a long list of prizes and awards that I've seen associated with your name. I wasn't sure what the most prestigious one is, but I thought the renowned Karl-Heinz Beckert's prize sounded like a pretty good one.
So it has a complicated German name, so it sounds good.
Yeah.
I don't know.
And that was for your work on trusted and trustworthy computing technology, and in particular its transfer to industrial practice. And I suspect we may hear a little bit of a number of things related to that today.
Yeah, okay.
So with that, I'd like you to join me in welcoming our next speaker.
Thank you. Thank you very much for a nice introduction. It's always funny to hear somebody else talking about you. And I'm sorry, this microphone, this kind of microphone set looks like a televangelist. So, I actually like televangelists because they can manipulate people very simply, and it's very interesting to understand their mind and also mind of those people who listen to them. And we are talking also about AI today in some talks. So this talk is a series of talks that I started to put together last year in 2017, especially because of the work that I have been doing with a number of semiconductor industries, particularly Intel. And at TU Darmstadt, we have a huge lab for information security and privacy. There are 300 people who are exclusively doing research in security. German government has a lot of money, and they are giving us some money to do research here. And I'm going to go, I hope my time would be enough. I tried to make it high level enough because David told me how the public would be, how the attendees, what was the background of them would be, just through the deployed technology. And when we are talking about hardware-assisted security, we do not mean in general hardware security, because hardware security is a huge area. And hardware-assisted security means that you use features, security features in hardware, which is now very trendy, to protect your software. That is the talk is about, and it is about the deployed technology. The research technology, next year, you can invite me, I talk about the research. So, there is a historical overview. I just don't make it very, very long. Actually, it goes back to 1970, where you had a huge computer as a kind of, it's called Cambridge Capability System, and it has a memory isolation. We will come to that in hardware. Up to let's say, year 2000, where trusted platform modules were very hype and sexy. And today we talk about Intel SGX, the new security processors of Intel that are on the market for the last 2 years. And there were also other elements, the simple, like smart cards. When you have a banking card or when you have a payment card, you have these simple smart cards on them. And also there are, the mobile area was very, very active in this area. As David mentioned, I worked for Ericsson, and at that time, as I started, I'm not really very old, although I have gray hair, we had a huge mobile telephone like this, yeah? And we were making a lot of jokes about these mobile telephones. And today, people go to courses because they are addicted to mobile phones. And we could not think about that in, let's say, 20 years ago, even at Ericsson, a very advanced company. So, but what we are actually targeting, and this is why I think the industry is not going in a completely right way, is that in the last 3 decades, we are trying to do something which Bill Gates called trustworthy computing. That means you trust some elements in your computing device and you assume that the rest will be secure as well, because you built some mechanisms. And all is for protecting what I call, this is a picture from hacker community, what I call protect all the native code, all the legacy code, all the code that is written in C and C++, your operating systems. These are unsafe languages and they have lots of problems, and millions of code lines in every application are written in these unsafe languages, okay? So we are trying to protect an insecure system by adding some security features that we trust into our existing systems. I'm going to talk about these things, these technologies. I hope I will have time for that. And these are the real problems, because IT security is not only popular, but it is a fundamental thing in our society, because all these problems, like many of these technologies, are afterthought. They did not really do security by design. You heard privacy by design, but security by design. There is a huge amount of trust in manufacturers. We don't want that, actually. And there are the aspect of runtime attacks that I'm not going to talk about detail about, but I'm here. You can ask me detailed questions afterwards. And what we are going to have at the end of the talk, and it's about Meltdown, because the press makes a hype about it, and it is very, very serious thing, is leakage, information leakage, side channel attacks. We will come to that. Now, how do I evaluate that for students and some industry partners that they can understand it? I took the evaluation scale of President Trump. So, in all these problems, if I evaluate them like this. So, for example, there is a limited access by third party to these security technologies in hardware. Okay? But we have also academic research. And I'm involved in many projects, not only at EU based, but also international in Asia and also in US. And you will see that there are some names, because people try to give geeky and cool names to their projects that people remember it. And these are most cited work, these abbreviations. And if you look at those problems that we have, for example, let's say side channel resilience, we are doing almost optimistic, I would say. We are doing well in the academic research, but we are not doing well in deployment of academic research into the world of enterprises. Okay, so what is all about? This is an abstract view of your system. You have hardware and software. You have different kind of hardware, let's say, components. You have operating system and application, and what we want to do is to protect them against attacks on any of these abstraction levels. I/O, peripheral, operating system, like exploits for kernel, and application privilege escalations, and many more. And very recently, CPU. So I asked in the last 10 years in my lecture, my students, what do you think about when you get up in the morning before you turn on your smartphone or your laptop? Do you think, oh, I don't trust my CPU? I will not touch my computer? Are you that far in paranoia? If you are like this, then join the club, because the CPU is indeed under attack, and we all assume that our CPUs are trusted. As Chinese were making their own CPUs, I was involved in now I can talk about it, that's really funny. People in Western countries, they called their CPU, their secure CPU, and it is about 15 years ago, their Rice CPU. That was very insulting, but they knew how to control people when you control their CPU, because they can control the software and what they are using. Of course, they can also control where they can access the internet or not. But if you have control over CPU, you have control over the whole system. Go. But what we are looking for is this self-contained security. The green means secure. The orange means untrustworthy. So operating system is usually not trustworthy. It's a huge bunch of code. It's monolithic system. But we want to have, still we want to have security. And in hardware, we want to have a cryptographic key. We want to securely store it there. And those on the right are those properties we want to have. Isolation. So applications are isolated, in their memory are isolated from each other. This is the fundamental security principle. We want platform integrity. Is my platform changed from yesterday? Can I verify that? Secure storage. Where should I put my secrets? Device identification. Is it my device or a device from another one? Authentication capabilities. All these kind of things, these are the fundamentals, so to say, the basic principles for all the safe content security. So I want to come to one of the deployed technologies which was hype, and that is with this, maybe I show it here. This is how to put a key in the memory. And I come to something that I call it now meat. I don't know, has anybody heard about PUFs? Okay, we have some people, that's good. There are 5 people in this, they know about PUFs. So, as you see, I am a big fan of minions. Yeah, because PhD students are equivalents of minions. And good minions always write good papers and look for the right boss. So we are going to explain about physically unclonable functions. What is that? It was celebrated from MIT. I mean, the first idea came from MIT, and Philips, they had problems with that because Philips claimed that they had this idea as well, but they didn't publish it. Their own fault. They patented. So if you have a device or any physical object, you can extract from that physical object randomness. And from that randomness, which is called a physically unclonable function, we will come to unclonability. The noisy function, you can generate some through a stimulator, let's say challenge and response. You send a signal and you get a response back. You can extract a fingerprint. But it is a unique fingerprint for each device. Electronic chip is, for example, has a unique fingerprint. It's more complicated than that, but it's just high level. Okay? And then there are some properties. Unclonability. A physical structure cannot be copied because even 2 chips from the same type, they are different in a physical structure. Another thing is, it is infeasible to predict if I send a challenge and I get a response. It is infeasible to predict the next response if I know the challenge. And then it is tamper evident. That means if I want to attack it in hardware, for example, with a screwdriver, or try to open this chip, the physical structure changes, the randomness changes, the key or the fingerprint changes. So I will not get the same fingerprint, because from that fingerprint, you can extract a cryptographic key. But what is the advantage comparing to storing a key, as many companies do that? The advantage is that you don't have to store it. Whenever you need a key, the chip itself is the key. You generate it on the fly. So this is the reason why PUF was so, let's say, celebrated. Now, the problem, I'll give you an example. You see, you have a number of components. These components are called switches. And from the beginning, I give an impulse, and then I get a response at the back. These are a cascade of electronic switches. And you see that there are some lines inside these lines, yeah, so here. So if I give a challenge, these are 0 and 1s. Each switch lets either the signal going any path that in this are in these switches. For example, this is a switch, this is a challenge, this is a path that signal goes through, or the signal can go through this path. Yeah? And these paths are physically different. That means if you send the same signal, and this signal goes to, or 2 signals, they go through different paths, but the paths are never identical in physical material. This is the limit of physics. So let me show you that animation. So you go like this, and then you get a response. So the switches let with 1 and 0, let a path through, and then here one of them is faster than the other, and you get a 1. So your challenge is the vector C0 to C7, and then your response is 0, depending on which signal is faster. This property, which I explain in a very simple way, is used to make a PUF, and from these challenge and responses, you can generate a cryptographic key on the fly. So these are selected publications in the last years. I put them together from 2001 to 2017. And there are various kind of PUFs with linear functionality, memory-based PUF, delay-based PUF. For example, what I showed you is a delay-based PUF because there is a delay of paths. You calculate the delay, and then you make your challenge and response. So these different types of PUFs were generated because of a reason. What is the reason? Because we are talking about AI here, let us talk about the problem. Celebrated in 2000, broken the first physical structure modeling of delay PUFs was with machine learning in 2004. Very simple machine learning. It took 1 year to model a delay PUF. So these delay paths could be modeled in a linear way. So people could show that it is not really nonlinear. That was a big surprise. And then people started, and as you see, these boxes with dashed boxes, I can show you here. In this, we were also involved in a European project, Unique, which was actually the best universities in that PUF area. They got together, and I was leading that project, and we had very, very nice results in that project about the security of these PUFs. So it was not so celebrated anymore. And as you see, until now, 2018, there are papers how to break the last PUF that was proposed. And there are companies selling this to others. Okay? I don't say any names. So how did they break it? It's very, very simple, at least for Arbiter PUF. This is a simple example. Either you use modeling attack, just software, you just model it in software. You need, let's say, 10 to the power 6 challenge and responses, and you can make your model, improve your model better and over again until you can model the delay line. That is the W, the vector W. You can model this. But this needs a lot of challenge and response and may take 1 year. Another way to do it is to also physically attack that. That means you have a device, it has a PUF in it, you put a kind of photon emission attack, which I'm not going through it, but you can see under the microscope how these paths are taken. That is the amazing thing about it. And these instruments are getting much cheaper. So my colleague in Berlin, Jean-Pierre Seifert, has 20 unemployed physicists who are working day and night to break into any hardware that you can send them. So they really enjoy it. Physicists can do everything. Yeah? So that's why I like it, because physics is everything for me. So, and then combined with physical attacks, the time, so if here there is a long time, here you can have it maybe in 1 day, because you are also physically attacked the PUF. Now, I know that my talks usually are considered as very depressing. I don't tell you anything, so if you have a problem afterwards, just come to me, we can talk. But what you should know is that I'm not criticizing these technologies. They are fantastic technologies. I'm just criticizing that there is still work to do. Yeah? Okay, and just going back, there is we are now putting a real formal framework, because also proving the randomness, you must prove that it has enough entropy. There's lots of theoretical analysis behind it. All these PUFs have different models. There is no unified models, and we are making a framework for new technologies, memory technologies, memristers. Anybody heard about memristers? It's actually a kind of voodoo technology that doesn't really exist, but some companies are claiming that they are selling it, and based on that, we are trying to have a nonlinear behavior for PUFs. Okay, so Let me go to another technology which is now 15 years old, and that's TPMs. And there are still people writing papers with TPMs. Don't do that, please. Don't do that. So this is your system. PUF was a kind of hardware randomness, very low level. You have your keys inside. You generate it. Now people thought, let us do it differently. We add a cryptographic coprocessor called Trusted Platform Module. It has many cryptographic functionalities, and it gives me some guarantees. That means it can give me the guarantee that the right system is booted. The system that I trust. I can define anything that I trust. Yeah? So that is good, very nice, and IBM has done a lot of work in that, but also many other researchers, including my group. However, it gives you only a snapshot guarantee. They didn't think at that time about the sophisticated runtime attacks that are currently state-of-the-art, the so-called code reuse attacks. They do not inject code. They use the code which is available in your program memory. They chain that code together at runtime. You don't have to inject any code anymore. So the code reuse attacks don't change the binary. And all these technologies are based on the fact that the binary will not be changed. Because you compute a hash value, a cryptographic hash value of the binary, you don't need to know what hash value is. It's a mathematical mapping. And then this mapping remains the same, and you just compare that with the reference value, which is not the case here. When you have, let's say, when the hash does not change, but the attack is running. So, in summary, there are a number of assumptions that these things, now we know it, at that time people didn't know. And there are thousands of specifications from 230 enterprises that worked out the TPM specification. And there are many lawyers. And when lawyers come into play, I don't want to insult anyone, everything is screwed up. Because lawyers, they make the language, they make it flexible to have their own advantage. Otherwise, we don't need them. So, no insult, no offense, but as technician, you never talk to lawyers because then they start to ask questions which is not really comfortable. So, what is the problem here is that you have binary hashes that should express your, so to say, trustworthiness of the code, but the behavior of a code in runtime is not equivalent to a mathematical mapping. If you want to know why, code reuse attacks, and I can explain to you more. So, indeed, we know that all these things that we believed before, we have to view it a different way. So, for example, protection against software-only attacks was the goal of the TPMs. Today, you can also attack them in hardware. And hardware attacks are, people think it's more complicated. It is more complicated, but the tools are getting cheaper, as I mentioned. Now, we come to another technology which is 15 years old, and it's called Trusted Execution Environment. And I'm just going to talk about the mobile version of it, which is ARM Trust Zone. Who knows ARM Trust Zone? Some people, that's good. More than 7, okay. ARM Trust Zone, the idea is that I have a system, and at runtime, I can change to a secure system. I don't trust the running system, I change to a secure system from which I know that it is running in isolated way. That means the other software cannot access it. If I do online banking or do Apple Pay, my email application does not have access to the data of that application because it is security sensitive. And the promise is, these are the two systems. One of them is called the secure world, and the other one is called the normal world. The secure world is here. So anything that is running in that secure world, these are your apps. So for example, this is a trustlet. We call it trustlet because you trust it. This trustlet could be Apple Pay. It is running in an isolated area, physically isolated, so to say, memory isolation. So, and actually, from the beginning, in the time of Nokia, in the time that Nokia, you know this company, Nokia? Yeah? They were making really the best technology, I would say, in the world those times. They were a competitor to Ericsson. They used these technologies, even at that time, 15, 20 years ago, for subsidy lock, because they could put all the secrets that all the, let's say, features that do not allow a customer to change the provider in that secure execution environment, and the customer could not really mess up with it because it was protected. You needed high-skilled people. At that time, people didn't think that we will have very highly paid hackers that get maybe something else for $500,000 from NSA, if necessary. Yeah? So, and they are used for DRM. Mostly these things are used by companies. If you remember the FBI conflict with Apple is also coming from this principle, because the keys are in that secure execution environment that are connected to the password. I can explain that after the talk if you want. So the promise is I cannot access when that one is running, no other application can access this one. However, the problem is that if once I get in, I can compromise everything there. That is clear. Now, how do I get in? I just put 3 references from the last 3 black hats that people could copy any key which is in the secure world, because the implementation was buggy and they could find it out. But finding that out needs skill and talent. So, and then they could copy the key. This is one of the last attacks. And this copy the key means the key that encrypts all your hard disk, because Apple does a sophisticated technology for, let's say, encrypting your apps and the secrets related to it. This is the model of ARM trust zone. It's like old times in the Middle Age. So there's a king, and there are others, servants, so there's device. So ARM makes IP. I think ARM doesn't have any engineers anymore. They just make the IP, very, very smart business model. Device manufacturer make the chip, put it in your smartphone, because all smartphones, nearly all smartphones have ARM trust zone, and network providers have limited access to it. But the problem is, Claudia was talking about privacy, is that app developers have no access to this area. If they have access to this trusted execution environment, they can make many things more private. This is not possible because of licensing and because of other problems. If 2 apps are running in this secure execution environment, one app can attack the other one. So Apple wants exclusive right. This is why they do their own hardware. Coming back to that, it's an old technology. I think it's a very good technology. The implementation of the secure world has been attacked many times successfully, depending on the company. I don't want to say any names. But the positive part is that trust zone, with the old idea, they still can guarantee secure I/O. Secure I/O means, is that the right window on my small mobile phone that I am typing my password in? Is that the right one? How do you know? You don't know. Is the device that I connected to my smartphone the right one? This is what we can guarantee with properties in trust zone. The last part of the talk is about Intel SGX. So, standard question, who knows Intel SGX? Also some people. I'm very happy that at least, yeah, okay. So, again, we come back to our system, abstract representation of it. Now, the idea of SGX is something using, it's a generalization of trust zone. Now I have many different trusted execution environments that I call enclave or enclaves. In these green parts, I can run any security critical operation. If I want to do a digital signature, if I want to encrypt and decrypt, if I want to do privacy preserving computation, if I want to kind of protect my IP because I don't want to give out my AI algorithm, it is running in that enclave. The orange parts are not trusted. That means the clue here is that SGX promises security even in the presence of a malicious operating system. That is a big word. Operating system is the master over hardware, so to say. Now, we will see that this is not completely true, and that is kind of curse. So the adversary model could be a curse for you. So how? The promise is these enclaves are like physical memory that are assigned to them is separated from any other application, even from operating system. This is the promise that they give. Now, the problem is that we will talk about it, the side channel attacks, as I said from the beginning, and this is what goes direction meltdown. The side channel attack was not included in the adversary model of SGX. They knew that side channels you cannot prevent in general. And we will come to that, what it means to have side channels. What does it mean actually? So, however, the extent, the consequence of side channel attacks was not clear at the time that Intel was making SGX. And SGX development needed 10 years. Semiconductor companies, they do not do one-year things. And you have to convince the business department, because business unit is even worse than the legal department. Sorry to insult some business unit people here if there are some. Because they don't, most of them, they don't know technology, they just see dollars, yeah? Which is okay for a company. Okay. Now, there are also code reuse attacks. I will not go through that, but as I said, you can ask me. So that, for example, copy a key from the using side channel attacks and code reuse attack, copy cryptographic key from the inside of the enclave to the adversary. And this is the reason why meltdown exists now. Yeah. This is SGX. Meltdown is not against SGX, but there are now currently attacks against SGX as well using meltdown and Spectre, because it is against CPU. When you have the CPU memory, then everything's over. Okay, so let's talk about the leakage in general, but also in SGX, which promise you confidentiality of operation in these enclaves. So one of the attacks that was published immediately by researchers and was taken very seriously by Intel was the so-called page fault attack. What does it mean? If you look here, this EPC, which is for enclave page cache, it's a specific memory area for those enclaves. They are reserved only for enclaves. And if an application has an enclave, what they did, they said, okay, we are going to unmap this memory. And the problem is that the operating system still manages the memory, cannot look into the enclave, but it manages the memory. So there are page tables. Oh, sorry. If I unmap all the memory of enclaves through the page tables, so I just, let's say, unmap them. That means I occupy them, so to say. And then there is an app or enclave that there is an enclave wants to use the memory is unmapped. So there will be a fault handler, that's an interrupt. It says this memory is not accessible by you. And this fault handler is, so to say, triggered. Now, what people did is that they looked, what is the access pattern to this memory? Because they see enclave wants to access the memory, these memory cells, for example, or these cache lines, and they say, no, there is no access to it. So you see the pattern. Oh, why is this? Okay. And what happened is that the computation that is running inside the enclave is hidden, but the access to the page faults, you could see the access to the memory. And if you know what algorithm is running in the enclave, for example, a compression algorithm, the picture is the secret. The compression algorithm, JPEG, is open. So you know how JPEG works. But the picture is secret. So this is what they recovered, just by memory access. Yeah? The next thing is even worse, and that is cache. I think most of computer scientists know what cache is. Cache is used for efficiency for the CPU. So CPU, before you go to main memory, you just cache it. Yeah? So, and enclaves are also using cache. So all processes and enclaves are using the same cache. And if you are sharing a media, then there is a side channel. So you can observe this cache and extract information from the enclave, although you cannot look into it. So, and this is why cache attacks are very important also in this context. Cache attacks are known for more than 20 years. It's not something new, okay? But it gets more interesting if somebody wants to sell you something which claims security, yeah? And in shared media, you have a problem. Okay. Now, I sum up the recent attacks on SGX. As you see, we have different caches. Cache level 3, cache level 2. Level 3 is a very slow cache, but it's bigger. Level 1 is a very fast cache, but it's smaller. This SMT means simultaneous multi-threading. That means there are 2 processes running on each core. So there's a multi-core system. Now, people used all these caches, level 1, level 2, and level 3, but also things like branch predictions. You don't have to know what it is, but the CPUs have branch prediction. They just predict what kind of branch comes next. Yeah? And they used all these cache accesses to find out a cryptographic key of RSA algorithm that is running in the enclave, extracting the key by just seeing the cache access. They used, so if you see here, something that people use in cache attacks is called prime and probe. That means you just observe the cache, so the one application observes the cache access of the other application. That is called prime and probe. And with that technology, you filter the noise that it is in the cache to understand if the accesses are from this specific application. So this technology is used to do many things, and I'm just showing you that different caches and branch prediction, those tools that CPU is using are used against the enclave. And there are also attacks that use one enclave against the other, one enclave against the other enclave. That is even cooler. So one problem with all these attacks is that they interrupt the enclave. They use enclave as oracle. They must interrupt it, analyze the memory, run it again, because you have access to your device. So you can build mechanisms against it. If you see, oh, the enclave is interrupted, it could be an attack. Now, we were looking at that in our group. Of course, we also provide that to Intel, that we can also do that without interrupting the enclave. And what was interesting here is that we didn't only extract an RSA key, which is 2048-bit from the enclave, but also we could run so if you run a genomic application, genomic sequencing application, and the genes or the gene sequence is, so to say, the secret. So they are running in the enclave. Now, we could extract a specific DNA from the enclave, although it is an isolated, physically isolated memory, but by just looking at the cache. It's too complicated just to explain it in the next 7 minutes, but if you want, I can show it to you afterwards how it works. It's really nice because the DNA that are used to identify people, you need some knowledge about DNA extraction, but you can get this information out of the cache. Okay, so there are defenses, of course. For those who are interested in this area, there are defenses, but all these defenses use technology like, for example, TSX that goes too far. It's called transactional synchronization extensions. That means when you have a number of cores, and you want to use the cache, this technology coordinates that so that it does a speculation, and then if the speculation is right, you are fast. If it is not right, it's rolled back between the cores when they want to use the cache. They use this technology, let's say, misused it, to protect it against attacks to enclaves. But as I said, these are the publications on it, but those techniques, the cloak is from Microsoft, those techniques have the problem that they either need to slow down the enclave, you can detect it with intrusion detection, or they interrupt the enclave. And many systems do not have this TSX functionality. So now you ask, is there any solution against side channel attacks on shared media? General side channel, not SGX related. Yes, there are. Write programs in a side channel resilient manner, privacy preserving programming. Very hard for huge programs. Very efficient, very effective, so to say, for small programs like crypto libraries. When you want to encrypt, the algorithm is very simple. You can write it in such a way, but not for others. So, monitoring the attack effect, as I said, you use other technologies to monitoring the effect. This is in general very hard. Intrusion detection, still, we have problems with it. Then there is a solution which cryptographers look, because it actually has no use in practice, but it's very nice cryptographic game. That's the difference between practitioners and cryptographers. And I was myself a cryptographer. And I decided to go to security because either you die poor or you get more funding for your students. So it's called oblivious execution. What does it mean? Oblivious execution is it means that if you access the memory, not only memory, if you access a database and the adversary is observing your accesses, it can infer information. But however, what is if you access the memory, all memory at the same time? Then the adversary doesn't know which memory you like more, which memory you're accessing. This is the effect of oblivious RAM. Now, if you access all the memory, you have linear complexity. But then some people started to think after 20 years, with lots of, let's say, aged PhD students, they could find a sublinear efficiency, which has a certain limit. After that, it is again linear. But it is more efficient, but it's awfully inefficient. If you want to use this for SGX, you get up to 600 times, in the worst case, more overload, 600 times. So I don't think that I saw indeed a marketing thing by Nokia. Finnish people, in the time that I worked for Ericsson, Finnish people who are really calm people, they get very angry if you have to wait for their phone more than 35 to 45 seconds to get a response. So if you have a system that is 600 times has more overload, I don't know what happens to those Finnish people. So anyway, so the conclusion of SGX is that it is a very useful technology on one side, but researchers are smart. And it is very, very bad thing that industry, especially in Germany, thinks that researchers are dumb. They just want our researchers, or so to say, students, but researchers, they just do something. No, 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 no. This is a technology which is deployed. I didn't talk about any research, academic research that is not used. You can talk about it. I'm involved in many of them. I'm just trying to show you. And I'm telling to Intel as well. And this is why they have always supporting researchers, but also business you must understand. You must listen to researchers because at the end they come with a broken system and that's it. Everything is over. So let us go to the last part, the last 3-4 minutes. Maybe you are interested in this. What is actually Meltdown and Spectre? So we talked about side channels. We talked about information leakage through caches, through computation. And now we are going to talk about something that is in the press, and I think in 2 or 3 months, everybody will forget it, but Intel will not forget it. So this is some news. I mean, this is press, of course. You don't have to trust what they say, but okay, journalists like stories, and they put it in a newspaper. That's good for researchers. But what happens is that, why is that possible? I just try to very simply show why is that possible. Assume that you have a malicious application. This application is very, very evil. Yeah? And you have a victim. This victim could be any application or even operating system. So this malicious user, I said user because it is in a user space. It's called user space and kernel space in a practical world. So this application wants to access something in this that this victim has. And this thing is, for example, a cryptographic key. It could be password, it could be a privacy-preserving computation. Now, usually, the computation always puts something in the cache, and at that time, you can access the memory. This is not privileged access, because if the key is in the kernel, a user application has never the privilege to access a kernel module, okay? Now, the problem is that after this isolation, you say everything is good. The problem is the so-called speculative execution. And I compare it to Wall Street. Speculation is never good. It will lead to meltdown, yeah? So what does the CPU do? The CPU speculates. It says, oh, I see this instruction, I go further. The application doesn't go further, but they go further, further, further. They also bypass many, so to say, many rules, because they want to speculate. They see, I must be faster. This is why Intel selling fast processors. But these algorithms are not always open. So researchers cannot jump on it and say, oh, I saw this. They have to reverse engineer, and this is unfair. We must reverse engineer it, the whole, so to say, I would not say bad design, but speculative design, yeah? So now, speculative execution goes further, but and if they are wrong, so the calculation goes maybe differently. If they are wrong, they roll everything back. But when they roll everything back, they forget one thing. They leave the data in the cache. So, and then the adversary user that has not actually no access to this key, it can now access to the key because any user can access this key. This is the very simple principle of it. Let me go to more details. There are 3 attacks, actually. The first attack is when you use the data which is in the cache. It remains in the cache when the speculative execution is over. The second one is when the speculative execution bypasses the bound checks. For example, you have a input. The input should be 10 bytes or 10 bits long. And speculative execution forgets this. Just say, I want to go further, up to 9 steps further. So it over jumps these bound checks. The third one, and the more complicated one, is exploits that inject branches. Forget about that, what injection branches mean. It means that speculative execution allows to execute code that actually you should not do, and if you do it, when you roll back, you should not forget anything. So the adversary can influence where your program jump at the end. And that could be a jump to an address which is very, very sensitive, for example, a cryptographic key. Okay? Okay, maybe I'm boring you because I see the faces. They're saying, I know that some of you are thinking, where should I go next vacation? What is this guy is talking about? Yeah? But it is over in just 2 or 3 minutes, don't worry. So there are 3 attacks, but there is one bug. And I want to go a bit into details. Please, I just ask for mercy. It's not too much detail. Let's see what is the bug actually. For those who are interested in computer science, we have again privileged memory. Privileged memory, that means an application is allowed to access the memory or not. Like operating system allows to access some memory. Then we have cache, as always. And then we have a register. This register is used for many things. CPUs have registers. So what happens is that the adversary says, hey, I want to access this sensitive information. We call it kernel address. You see in the parentheses, this one. Yeah? This is not allowed because adversary cannot do that. We assume that that is right. Now, so as you say, the first step is illegal memory access raises exception. the operating system said, no, 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 I don't like you, you cannot access this, yeah, to make it pictorial for you. Explaining to your kids is very, I mean, I have no kids, but I have PhD students. Lots of them. Sometimes you have to talk to them like this, and then they come to the idea, and then you learn from them so much. I learn every day from them. So now, you write, the adversary writes this piece of code that you see there. Forget about what it is. It just tests what is the value in the register. Is it 0 or not? If it is not 0, then it goes further, and what happens here, it takes the register value, it doesn't know what is inside. It just takes the register and adds it to an address area. Why is that done? And it puts in that address area the value 1. Why? Because the adversary wants to mark the values that he or she does not know now, but it just marks it and say, I want to come back to calculate, to do a reverse calculation from a 1 and 0 and 1, 1, 1. This pattern, from this pattern, I go back and calculate what was actually in that register. That was in the kernel address. For example, the address of a cryptographic key. Okay? This is the speculative execution that very simple, actually, okay? From the view of skilled computer science, is very simple. Now, this value is put in the cache. So this 1 is put in the cache. And if you run that like an oracle again and again and again, each time you get some bytes of that address of this address that you assign 1, 0, 1, 1, 1 to it. And these are all in the cache. But they remain in the cache when this speculative execution rolls back and the program runs. And then there are other techniques that are used. These techniques are known to analyze this cache, because the cache has also other processes in it. That means there is a noise. You have to filter that noise. But the adversary knows exactly this pattern belongs to that register and calculates it back to find the value. Okay. So I am in the last 2 slides or 3 slides. Fixing is hard. Intel started to fix it very fast in software. So Meltdown is an attack in software. Spectre is an attack which is more, you need to change the instruction set. Now, a fast fix even brought Linus Torvald. This is a Finnish guy. Very angry. Because he didn't like, look what he did. Actually, you don't do these things. In America, I should say beep here. Yeah? So he was very angry because he said that the patches of Intel are really, I'm sorry to say that, crappy. Yeah? Because they were attacked as well. Now, there are solutions for the Meltdown, which is more attacking to the kernel, and these solutions were known even before Meltdown was known. One of them is from our group, one of them is from those guys who were also involved in the 3rd phase of Meltdown from Graz. But these are not efficient solutions. Between 5 to 10 or sometimes 20% overhead, and this is not acceptable for many applications, okay? But they are patching, at least for software, many systems. Now, what should we do? There are solutions for it. Either the source code must be changed, or you need compiler support. All of these things are more complicated. And if you want to know more about it, I can tell you more after the talk. So, alternative solution, that is interesting. A Chinese company claims they have the original and secure Intel processor. I'm not joking. This is German, but this is indeed what they are selling. I'm not just joking. This is indeed a company that says, we don't have these problems. And I think, as the last word of this talk, I really believe that companies need to invest more in researchers, not tell them what to do, but just listen to them. And that's huge value that you're not going to pay for it so much. So Intel listens to many researchers worldwide, but still there are IP protection aspects, there are business unit aspects that should be taken into account. On the other hand, it is good to have a very, so to say, very close collaboration with researchers, that these problems would not happen because we know the solutions. Another architecture or design, but they should listen to that because, as I said from the beginning, legacy protection is good, but we need research for new things. And this is what also at conferences, top-tier conferences, still not understood, that we need new constructions. Thank you very much.
So those of you who remembered that we had it was hashtag DigiChalmers, I'm sure got quite a few entertaining sound bites to pick from there. But I thank you for a very enlightening and an interesting talk. Do we have any questions from the audience?
Please. I think he needs a microphone.
Picking up on your last invitation here to focus on future research in this era, what is your opinion and your prediction regarding the possibilities of using quantum entanglement for the cryptographic parts, especially for side channel inspection? There's been a lot of I should say, speculations in this area over the last decade. But what is your personal opinion on these possibilities?
So I am not a physicist. As I said, I like physicists. Quantum entanglement, it depends what you are talking about. You're talking about quantum computing and quantum entanglement be used to prevent the side channel attacks? Okay, indeed, quantum entanglement says, if I see something, I don't see it. Something like that. So you don't really have side channels. However, if you put quantum, let's say, there are many researchers who are doing quantum cryptography. First of all, it is extremely inefficient. And second, many of these quantum crypto-based systems are not, so to say, are not secure against active adversaries. So passive, yes, but active adversary when you are attacking a system at runtime. Why I'm saying that? Because the underlying technology is, of course, quantum-based, let's say in hardware. You may not get all the side channel attacks that you can get here from the hardware, you're right. But on top of that, you have operating system, you have application, you have shared media. Unless you say, there are solutions now with commodity systems. Don't use speculative execution like it is now. Just add access control, which means less efficiency, but you don't have to repair all this system in the next 20 years. As you know, for companies that doesn't matter. I mean, Intel is really, I know it from internal Intel, they are really, really concerned about that. They are professional in that sense. On the other hand, tell you a company like Volkswagen, they did deliberate cheating, and they are even earning more money than last year. So they have their new results. So that means companies will have short memory, and consumers as well, until the next attack. But yes, side channels, you still cannot get rid of them, even if you use quantum entanglement technology. You can reduce it, but then you have the problem of quantum technology that is not really in place yet. But, of course, it's one solution.
Okay, I think in the interest of time, we'll need to leave it there, but thank you again.
No problem.